Okay, thank you. So we can slowly shift to the discussion. And actually, I mean, we have some transition here, since there was a question raised by Matthew Smith in his talk. There was about should we rewrite the DFT Planewave code? And I mean, here you can already give your own view on that, Bert, since you have a DFT Planewave part, if I understood correctly, in WChemX. So, I mean, and is C++ a part of the answer as well for the Planewave codes?
Well, I can tell you that we did rewrite the whole Planewave code from what was Fortran to C++. And again, it's a choice, right? It depends, I would say, the choice between rewriting or modifying depends a little bit on where you are with the software stack. Remember, NWChem was 20 years old. So there is a large amount of legacy. And
most of the Planewave codes are also that old. Huh? So
exactly, that's true. But I do have to say there is some more recent codes out there, right? So if you look at computational chemistry, there's also more recent codes out there that are C++ based. Sci4 is a good one. Hey, PySCF is completely Python, right? So people have taken longer, different approaches. But what's interesting with those codes generally is that they are not running large-scale parallel simulations. So we're trying to bring pieces together that are a little bit more challenging. It really depends again. So I think the Planewave codes could have gone either way. Although, because the data structures in general, Planewave codes are not as challenging. Well, I should not say that they are challenging anyway, but they have not changed as drastically when it comes to thinking about sparsification, right? So, and getting more sparse methods. The Planewave is what it is. Gaussian places that you can do a lot more crazy things. You can just go and drop stuff. If we would have gone with a Planewave code that was numerical grids, that's a different story, because there's a lot more you can do when it comes to the grid points and how you move data around. So it for us, the Planewave code is because it's actually interestingly written, because it's Eric Balaska who wrote that C++ code. It's very much structured similar to what a classical Planewave code would have looked like, just in C++. So they are not. He's not taking advantage of some of the auto code generation that we do actually in the Gaussian part of the NWChemX code.
And if I may extend the question to Erwin, in the sense that, I mean, if we go beyond the Planewave code and we see all the DFT code, is the fact that they are written in Fortran, is it some kind of a problem in the long run? Is it difficult to find the developers for Fortran, or, you know, rewriting that in a different language like C++ might be one way to go?
I think it's definitely a problem on two sides. So you said finding good Fortran developers is getting increasingly challenging, right? People are not taught this anymore at university, and they probably learn them during their PhD or even only at the postdoc level. And then, of course, the level of knowledge kind of is limited, right? And I think Matthew has shown this pretty well, that the modern developments with GPUs, what NVIDIA is doing, but also what Intel is doing, they are not focusing on Fortran anymore, right? When I talk to Intel, and as Bert said, they're going SQL, yeah, perfect, wonderful. And I asked them, so what do I do with Fortran codes? They said, oh yeah, Fortran codes. Oh well, I use OpenMP. That's fine. Yeah, it will work. Yes, it will work, but will it be performant? Yeah, that's remains to be seen. So I've also examples back from KTH where people worked actually, Bert, you might know the code, it's part of the ECP project, the NEC 5000 CFD code. And well, I think there's still discussions going on, but at the end, the KTH team decided if we really want to go to GPUs, we have to do this in C++, right? There's no way we do this in Fortran. So they are currently in a kind of hybrid mode where parts stay in Fortran, parts go in C++, and whether this eventually will end in a complete rewrite remains to be seen. But I think particularly using GPUs and other modern things, there will be more hardware coming, and the memory layout and all that. I think it will be very difficult if you just stick to Fortran.
Matthew, since you raised the question in your talk, maybe you can give your view on the topic. And anyone can chime in and give their opinion as well.
Yeah, sure. Well, it's interesting to hear people talk about it at more of a macro level. I mean, I'm interested to know in rewriting the Planewave code. I mean, how much work is involved in that on the scale that you're talking about? Are you essentially saying, right, well, let's just rework this from scratch? Is that what it takes?
Well, that's the impression that was given by Bert in his talk. That's what they did for NWChem-X.
Yeah, so that one was completely rewritten in C++, yes.
Yeah.
But that was actually, so it's interestingly, so the Planewave code is a single person effort within in NWChem-X. So it wasn't that big of a effort to do. But again, it's just a straight rewrite. I think one of the things that one really should think about is, what is the goal of the Planewave code? Is it the goal to get performance out of the next generation piece of hardware, or they just want to run science simulations? If it's the first one of the things that you see a lot of in the ECP project is code starting to think about what I mentioned already before, finding a level of abstraction away from the specific CUDA, NVIDIA, CUDA, SQL, hipster type languages. So find a way to have a higher abstraction, because that's where the scientific development needs to happen. And then rely, and it will never be perfect, but rely on those lower level translations to the specific programming languages, because that allows your code to be as agnostic to the hardware as possible. Yes, you will not get the maximum performance out of it, but you need to spend an awful lot of time getting performance out of hardware. And the question is that really the goal of the code that you're developing? In a lot of ways, your goal is to deliver science, do science with your code using the latest hardware. So my view has always been is you probably need to try spend as little as possible on the hardware specific stuff, and as much on providing a tool set and a infrastructure that allows developers to focus on the science. And NWChem initially tried to do that with the global arrays framework effectively, right? We don't have to worry about parallelism to some extent. We just use the global array framework. But this was within the Fortran era effectively, and in a very abstract object-oriented way of thinking. It worked reasonably well, but heterogeneity and concurrency just have defeated us in the original code by now. So that's why we chose to do the rewrite, because of the scales of the problems that we want to run. I think if we go back, if we take NWChem-X when it comes out and you run it on a small platform, it's not all these challenges with hipster, CUDA, and so on are not going to be the challenge. It will perform on small platforms simply because it's not going to be that different in a hardware sense. So honestly, yeah, you need to think about, if you want to rewrite something that allows you to abstract away from the hardware specific pieces.
Matthias?
Yeah. So a question to all of you guys. I mean, basically, long ago when I did my PhD, Fortran was already dead. But I mean, it is still there, and the reason is that the compilers were really always a little bit better than the other ones. Actually, in some intermediate time, even much better than other ones. So my question is really, if you nowadays would do these things in Python plus C++, so really in this combination, which fits together well, are there really compilers which are comparable to what we are used to in Fortran?
Well, the problem is that not all platforms even have compilers, right?
Yeah.
That's the real problem, is that a lot of vendors don't care.
Yeah.
But
Okay.
I think one of the issues is not so much the compiler, but it's the programming style.
That's
You can program C++ very efficiently.
Mhm.
And you can have pointer redirection all over the place, and you're just chasing pointers, and then the compiler can't do anything. So I think it's a lot also on the programmer to make the programmer program in an efficient way, so the compiler can generate efficient code. Fortran didn't allow you to write in an inefficient way. So that was the good thing about Fortran, or is the good thing about Fortran still.
But shouldn't a good compiler solve a lot of these software hardware problems? I mean, can't you really shift some of these problems to the compiler level?
Well, that gets back to it. If we abstract it to a level that that the compiler can do the rest, yes. And that's what you do see. So there's in the software infrastructure of ECP, they are developing kind of those intermediate levels that provide us the tools to go straight to the low level, and then the compilers know what to do. It's that kind of the C++. Yes, we can go crazy in C++, so you have to not do stupid things. Don't think like a human, think like a computer when you're programming, right? But in the long run, there needs to be a level where we program and a compiler takes over. And if we dive too low, then it takes us more effort. If we go too high, it takes the compiler too much effort. So there's always we need to find that happy balance, and I don't think anybody has really found that kind of middle ground where we can get the maximum performance out of a compiler. And that's why you see all these different programming languages show up too, because effectively what they do is they kind of constrain you back. They take C++ and constrain you back to what they want you to do so that the compiler can do the best thing they can do.
I think also we'll see more of the.
Yeah.
No,
sorry.
go ahead.
Yeah.
Claudia,
go ahead.
Actually, related to this, some people tell me that Fortran 2018 is another big step forward, and that's why I'm a bit surprised that that Fortran is again predicted to be dead.
I'm not saying I have not said it's dead, right? But it depends on where you're going, and the vendor support is diminishing. That's definitely what you see. And yes, the standardizations efforts, they are going on, and Fortran 2018 is probably a step forward. I haven't followed it closely, but will the vendors pick up on it? Will there be efficient implementation? That remains to be seen.
Yeah.
I hate to say it, but the higher level the Fortran code, that the higher numbers in the Fortran standard, the closer they come to C++.
That's also true.
Phil?
Thanks. Yeah, just on that note, really. I mean, 10 years ago, we were asking Intel about compilers, and they told us that the C++ team, depending on how you counted it, was 28 to 50 people, and the Fortran team was 2. And Fortran beat C++ hands down then. But 10 years of that kind of efforts going into a compiler, and they're surprisingly close. So to go to your point, Matthias, you would be surprised what a C++ compiler could do with code that you would look at, humanly and go, well, this cannot perform well. But the compilers can, especially with templates and some of the modern C++ abstractions. But they're coming into Fortran, and there's also FIP, the Fortran preprocessor, which can do some templating things in Fortran and other nice things. But is there a Fortran 2008 compiler, fully compliant? I'm not sure there is.
But actually, I also asked about
count
this
the cross
combination,
compilers.
right? I also asked about, say, the combination of Python and C++, which people usually like very much. But would that also be fully supported by modern compilers?
I think that would. I mean, the route we're going is Python with Fortran. So we're taking that route, we're sticking with Fortran kernels and then letting scientists stitch that together in Python. And now Fortran is interoperable with C and C++. That means that actually they can interoperate at a low level or a high level. We can interface with system level kernels within Fortran now without having to jump through vendor specific hoops. So I think if your design is right, you can do good things in most languages. Or to repeat an old saying, a good programmer can write Fortran in any language.
I second that.
Yeah.
If I could make just one small comment. So there was, I can't remember who said this, but someone was saying that the focus of the scientist is on running software to get science. And I absolutely agree with that. And you might ask questions like, is it worth 12 months of a postdoc or a research software engineer in your group to get a 5% performance improvement or something? But if you move to someone else, like someone running a tier 0 or tier 1 HPC facility who might have 40% of their cycles in VASP or Abinit or Quantum Espresso, if you start saying, would you like an extra 5% of your facility, that's a much more attractive thing to them. So if you can have 5% of your machine effectively for, say, 12 or 24 months of person effort, that's very attractive from a supercomputing perspective.
Absolutely, Phil. I think that's a key point. At the end, we're talking money, right? And 5% of an exascale machine costs a hell lot of money. But what you are pointing at, I think, is really something the community needs to think about, and this is getting more professional in software development. Of course, if you have a material science postdoc, that person is supposed to do material science and not optimize the code 90 or 95% of his or her time, right? So I think we need to get there that we have more of these professional academic software engineers that work alongside the scientists, but take away the heavy lifting from the scientists so they can actually do the science.
Hear, hear.
Matthias?
Yeah, no, I think actually these developments require probably really the combination of good scientists. I mean, good scientists always had to write these codes because you need some concepts which has to come from the science, but having more support really from software engineers is exactly what we need. And this is actually also how Erwin's team is operating, which is actually great. I'm still wondering actually, I mean, as we said, I mean, there is, say, which when I was younger was Amdahl's law, and somewhat we are fighting with this when we say about workstations, workflows. Does it really make sense to have an exascale computer, or is it better to have 1,000 petascale computers? So what is cheaper? I think for the scientists, 1,000 petascale computers would be more efficient.
Matthew, I don't know if you want to answer this question or if someone else wants to answer this question.
I think it was more of related to a question that I wanted to ask rather than answer. In fact, it relates to a question I wanted to ask, but in particular, he talked about designing the code to be a thin layer for the to be optimal for whatever the hardware is that you happen to have at hand. Because what we should be interested in is the time to science and just getting the science done, and fair enough. But I wonder how, if you pursue that as a policy, do you not run the danger of ending up with software that really isn't using the hardware to the extent that the hardware is capable of to the point where actually you are just wasting money, and you say, well, why do we have all this hardware if we're not actually using it? Is it just a case of, well, that's what's there and it's being used in other fields, therefore that's what we end up using, and therefore we don't really care? Is that maintainable? If that is the end point of that kind of approach, is that maintainable? I'm interested to hear what you think.
Well, it has been, so NWChem has been maintained for 20 years, but we had a lucky source of continuous funding, right? We were part of a construction project at that point in time called the Environmental Molecular Sciences Laboratory, and we were kind of an instrument. So we had continuous funding. That allowed us to actually develop the code and maintain and get it ready for the next generation platform. That kind of support is going away. It just doesn't exist anymore. So a lot of our software development efforts are going to be very project-based. So it's going to be science-driven. So these ECP projects, these kind of construction projects, are a unique opportunity, and isn't a unique opportunity for us as a entity, as a group, to really kind of build that next generation construction project code and hope that we can then use continuous project funding to advance the capabilities. But the problem is we'll never have, again, really a constant set of funding to continuously improve the code with the next generation hardware platforms. So that's why we chose to get an infrastructure that is, and build an infrastructure such that we can get the performance to a level that is, I would say, good enough. Sure, we can go still to a HPC supercomputing center and say, hey, if you put some people on there to get more performance out of this part, you might get more bang for your buck. But that is going to be harder and harder for the scientific development teams. And so there is also a very conscious reason why we chose to build, yes, we're going to build an exascale code, but we are very conscious of how much we can get out of a single node, how we can get out of a single GPU. Because as Matthias was saying, is the question, is an exascale computer going to be the best thing since sliced bread, or is it 1,000 petascale computers, or even 100 petaflop computers better? We have, NWChem has had a user base that goes from a workstation to exascale effectively. So that's always a challenge, has always been a challenge. We have marketed us as scalable code. That means you have a user base that is broader. If you don't have that marketing, then it's a little easier, I think. But reality is there will be exascale computers, but there will be few of those. We need to be able to run at a petascale. And what's interesting is, even though we're developing our exascale code, reduced scaling methods, we already know that it's going to perform at petascale performance. So this provides us some comfort that there is a way broader user base for all the smaller systems that are going to be available in the long run. And yes, there will be only a few exascale machines. Simply the power, the cost, it's just not sustainable. So we will be ready. We are ready for petascale. We've been with NWChem already at the petascale, but we're definitely getting more bang for our buck with NWChem EX when we have petaflop machines.
So, Bert, I second most what you said, right? But say the cost, whether you have one exaflop system or you have your 1,000 petaflops, your energy bill will be the same. You just don't see it, right? Because you distribute it over 1,000 sites.
Sure, fair.
Yeah.
Fair.
So, but at the end, in the global view, it's the same. But I agree with you, we'll only see a few exascale systems. And I think for me, the reason is that typically you try to leverage economies of scale, right? And to build larger systems, typically it's more efficient. You need fewer people, you probably get a better hardware deal and so forth. With exascale, we are getting into dimensions where I'm not quite sure these economies of scale still hold. Yeah, you need to invest so much to get the electricity there, to get the cooling there. We're getting into dimensions that are really enormous. Yeah, and that's why I'm not certain we can make this economy of scale argument. We can make it for the tens of petaflops, maybe for 100 petaflops, right? But for the exascale, I'm not quite sure. And I just seen it in other examples where people were thinking of how they get their computing hardware together and build a new large system, right? And just what they were thinking of, they're getting, yeah, well, we would need 20 megawatt. How many sites in the world you find that will say, oh yeah, I have 20 megawatts available, just come here, I run the system for you. It simply doesn't exist, right? And so this will be one of the big problems. But the other aspect, of course, is as you said, there are problems that require the exascale, right? And then, of course, it's a political question whether you want to give them their tool or not. But there is also and even more problems that require tens of petaflops or maybe hundreds of petaflops. And as we all know, if you have such problems running on a machine that is 10 to 100 times larger than your problem, your throughput is much increased, right? So that's another challenge.
I think the power story is not, I would disagree a little bit on the power story. So one of the interesting things with the exascale was that when the US chose to build exascale machines, they told the vendors they needed to have a power envelope of so much megawatts. What's the nice part of all of this is that all these vendors, they got money from the government to do that too, but still, all these vendors are now developing energy efficient processes. Mm-hmm. What's interesting, so it does have an advantage on the power side because these technologies will flow down to the smaller systems. So a petaflop machine or a 10 petaflop machine right now, its power consumption will be going down when they build the next. If a supercomputer center has a 10 petaflop machine and they buy a new 10 petaflop machine, their power envelope might be whatever, 50%, 60%.
Absolutely.
So it turned out that, yes, fair, if you have 1,000 petaflop machines versus 1 exaflop, that power, well, the power might actually be a little less on the exascale because cooling might be more efficient. But the advantage of these kind of efforts, these races to the exascale, have been that the power envelope across the supercomputing world has drastically reduced. So it was good.
I think we are in violent agreement here. So
yes, exactly, I think we are.
Okay, Matthew, you still have your hand raised. I don't know if that's remaining from before or if you want to ask.
So yeah, sorry. Let me.
Okay. So I think this is a nice point to stop. It was a very lively discussion. I'm very happy for that. So I would like to thank you three for your very nice talks and for this very nice discussion. I'd like to thank everyone for participating to this workshop. It was my first hybrid workshop, and I really enjoyed that. We had this conference dinner, which was something that we hadn't had for a long time, so it was great. And so I hope that you all enjoyed this workshop, and so I thank you very much, and maybe we'll see soon for another live experience. Thank you very much.
Let me just add a little thing. I mean, you know, there were several organizers of this workshop, but there's one person, and you know who that is, who really did most of the work. And I think the workshop was really very good. I mean, I've seen few workshops where we had so many high quality speakers. So, and for the work Gianmarco has done and put into this, I think we all thank him very much. Thanks, Gianmarco.
Thank you all. Thank you.
And goodbye to all of you.
Bye-bye.
Goodbye. Thank you.